Good morning. This is not the advertised talk, but the original plan was that I was going to have two talks, and I wasn't sure if I wanted to put them in one time slot or not. So this way, I have the flexibility to use the time how I want. But this is an update about imputation, which I talked about a year ago, and this is short information about some new functions to do this. And the focus here is on imputing from mid to high density markers, which is going to be very relevant based on all the talks we've been hearing on mid-density genotyping. So yes, this technology is revolutionizing plant breeding. Everyone wants to do this because it's really a great combination of having these genomics markers that allow you to do things like, look at relationships for quality control, linkage mapping, genomic selection. Plus, you can put trait-specific markers that allow you to replace the need to run CAST or other technologies for specific R genes and other quality traits. And the per sample cost allows you to screen large populations. The focus here is on the genomic selection application, and there are many reasons why you're likely to want to have to impute from a mid-density genotyping platform to a higher density. And I'm using the word trained population here in quotes. The concept is that you'll have some historical data that would very likely come from, let's say, a later stage of the breeding program than when you're deploying your mid-density, and you have the higher quality phenotypic data. You may, of course, have still some phenotypic data from the earlier stages, but imputing everything up to a common set of markers is necessary to deploy those prediction models. You don't want to take a prediction model that was parameterized on 10,000 markers and then just throw away, just not use the marker effects. You won't get the right predictions. You have to use a common set of regression variables across the predictions. So here's what this looks like in a practical way for our potato breeding program. We had a 2.5K 2,500 marker dart tag. This past year, we expanded it to 4,000 markers. We're using that in our first clonal selection stage. So for potato breeding, that means our first year in the field, we have a single plant. And then from those selections, we maybe have anywhere from 1% to 5%, depending upon the market type. You plant out in with multiple plants per clone, per genotype. So that's what a clonal selection trial or clone evaluation trial means in many different species. So that's where we're using our dart tag. This is 700. It fluctuates, but this is per market type. We have 3 market types, so we're having to do 1,000 to 2,000 samples per year, which is a good, reasonable genotyping budget for a small size breeding program at the dart tag price point. Then the following year, whatever survives that gets into what I call a preliminary yield trial, where it could be 1 or 2 locations, but you're now much more focused on measuring precisely quantitative traits like yield, dry matter, etc. And for that, at that stage, we're using a higher density platform. We have been using a SNP array, and now this year we're switching over to trying to use the sequence capture from the Rapid Genomics LGC technology. So I want to be able to genotype my candidates for genomic selection are that year 2 or clonal selection trial, and all my training population, which evolves every year, is based on largely the phenotypic data collected the following year on a smaller group of clones. So the tools to do this are available through the Polybreeder package, which you can go to my GitHub site. This is the 3rd vignette. The first 2 vignettes have been up there for a couple of years. Vignette 1 was an introduction to just how to use markers to look at genomic relationships and do some pedigree curation. The second vignette actually is about ploid determination and aneuploid determination. So we've been worrying about that in potato for a number of years as we transition from a tetraploid breeding to diploid breeding. So some different approaches than what Chris showed, but complementary, I think. And then vignette 3 is all about imputation and the use of variant call format. So last year I talked about this function impute, and the context was more for a RAD-seq kind of GBS, where any given sample, it's kind of random, any given marker it's kind of random which samples would have missing data. So if you look at envisioning your dosage matrix, it's like Swiss cheese, there's just holes everywhere, right? Now we want to specialize to a case where I have one data file, which is a group of individuals at the low density platform, and a separate data file on the high density. And the individuals that are in common between those two data files serve as the training population for the random forest algorithm. A random forest is a classification tree approach that makes these trees and then takes an ensemble average. And you have to have a set of individuals genotyped on both platforms for it to learn how to take the low density and predict the high density. So this is, inside of it, it's very similar to what I had before, but it's just organized based on how you're likely to have your data files. So your two input files can be in either a CSV dosage format, coded 0 up to whatever your ploidy is. It can be integers, it can be fractional values. There's different options there. Or you can take variant call format input files. The output file is a CSV dosage. But there are some functions actually in Polybreeder to convert dosage files to VCF and back and forth for those of you who want to do that. So let's look at a quick example of how this performed in a potato data set. This is tenfold cross-validation based on 215 potato samples genotyped with both the 2.5K dart tag trying to predict a 23K flex-seq. That's the sequence capture. And the result is shown with the y-axis being the root mean squared error for predicting the allele dosage. This is a quantitative measure of how close are you to predicting the dosage of, in this case, of a tetraploid potato, and it's a function of the minor allele frequency of the marker. And you can see the trend here. This is well known. The more variable the marker is, the harder it is to get the predictions right. Right? If everything has the same genotype, it's easy to predict it. You just predict that most common genotype. So that makes sense. The values here are still pretty reasonable. I mean, I'd like them to be a bit lower, but this is only 215 samples. The RMSE is somewhere at 0.6 at the high end, which means that, think about a 0.5 error is sort of, halfway between the integer dosages. If you rounded it, you would get the right answer. That's, an intuitive way of thinking about what does 0.5 mean practically. And last year I showed just how much better you can get with larger training populations with some simulation data. So if you had 400 or 600 samples, we would definitely expect those prediction errors to go down. So that's an idea. That's one option for using random forest. Now, random forest doesn't know anything about genetics, right? It's a machine learning algorithm. It's basically exploiting LD, although it has a nonlinear capability because it's not a linear prediction model. And we can do better than that, we know, if we use some genetic information. And so that comes into the picture when you have pedigrees and you have familiar relationships that you can exploit. And that's what linkage analysis is meant to do. It has a model of recombination. It's the same technology that goes into linkage mapping for QTL mapping. Now we're using it for imputation. And in diploids, especially in animal breeding, where they have these very large pedigree data sets, they have developed this to a real high sophisticated technology that combines both LD and LA, as they call it. We're not there yet in tetraploids, but we do have the capability to start to do linkage analysis as a gateway to this combined LD-LA approach. So this is a function in Polybreeder called impute_PO, where the PO stands for poly origin. That's the software that Dr. Chaoji Zhang over there developed a couple of years ago. We had some presentations about it at the 2021 workshop series, so you can go check out those presentations to learn more. And this is not really doing anything new, except, again, simplifying the process of organizing all the input files, creating the files that poly origin needs, running them in Julia, which is the platform it needs, and then taking the output and putting it back into a format that's convenient. So that's kind of what this impute_PO function does. And the software works for both diploid and tetraploid F1 populations, and you can have multiple parents that have been intermated to create a kind of arbitrary partial diallel mating design. So I want to show you an example of that here with potato, and just a bit about what the two kinds of input files you need. In this case, the high density file is actually just the phased parental genotypes. That's the information you need. You're gonna try and impute a set of progeny that derive from a set of common founders, and you have to have the phase SNP data for those founders. Now, in this case, this is the format that PolyOrigin expects. And at this point, the way I got this file was by running PolyOrigin on the high density markers. So that's kind of cheating. I mean, if you have the high density markers to begin with, you wouldn't be doing the imputation. Eventually, the goal is that you will just be propagating phased information down through your pedigree so that you won't have to use progeny to get phase genotypes. You will infer phase genotypes because they have been derived from a whole set of phased genetic analyses. So we're not there yet, but that's where this technology is going. The low density input file can be either CSV dosage or VCF. And again, you have to have already installed PolyOrigin and have that working on your computer for this to work. Installing the PolyBreeder package isn't going to do that for you. You have to do that separately. And there's tutorials about how to do that. So here's the data set. It's a half diallel with 5 parents. And you can see the family sizes range from 1 offspring to 20 offspring, which is pretty common for how many of our progeny make it to our clonal evaluation trial. So these were all potatoes in our clonal evaluation trial. And you don't need, once you have phased genotypes for the parents, you don't need any more. 1 offspring is all you need. You don't need to have a large family because you've already used the ancestral information to get that phased parental data. So here's the below the diagonal how the imputation error looks. These are root mean squared errors. So similar to what I was just talking about in the previous slide. The red is the random forest as the baseline comparison, and the values are all right around 0.95. So that's a little higher than what we saw in the earlier example, because this is a smaller population. There's only like 85 total individuals. And you can see in the green, the linkage analysis handily beat the random forest in every family. RMSE is just around 0.15. So I think this is a nice demonstration of hopefully what we're moving towards as we move towards phased genotypes in all of our breeding programs. So some concluding remarks. There's some other functions in PolyBreeder that may be very useful to you that I've used extensively. So there's this Dart2 VCF, which takes the Dart files that you'll get from DartTag, which come in these 2 different output files. It puts them together into a VCF file. Array2 VCF takes a Genome Studio format file and puts it into VCF. I don't use an Axiom array, so I don't know what that file format looks like, but we could write something similar for that if that were of interest. And then the GPS function, which has been out there for a year now already, takes a VCF file and then can replace any existing genotype calls with those based on updog if you want to do that. So I've learned and now made heavy use of VCF tools in my own program here in the last year. So if you're somewhat able to use command line programming, switching everything to VCF, this allows you to manipulate data sets, and you almost don't even need a database, honestly, at this point. It's so easy to keep track of these things if you're working by yourself. So I'll stop there and see if you have any questions about imputation. Thank you. Yeah.
You had the function mods_impute.
Yes.
From imputing from low to high density markers. That was based on block style. And then for the SNP array that we got, like we had different version of SNPs. So in that case, I used to use that function. So is there going to be update, or I can use the new function?
The question was about the older function merge_impute, which was based on a BLUP imputation. And that is now, I would say, obsolete. Don't use that. In fact, I just changed the documentation, the package to say, don't use this function anymore. So impute_L2H is superior. The random forest imputation will be superior. And as far as array versions, yes, in fact, that's how I have now combined the version 2, version 3, and version 4 array data is with the impute L2H. So that's what I would recommend doing. Yeah.
What about the runtime? So when you compare the random forest and the origin dash linkage analysis, take too long?
Question was about runtime for the 2 different imputation algorithms. That's these are smaller data sets, so I haven't tried to push it. I would say it does take longer to run the poly origin version, but not a lot longer. On 4 or 5 cores, the results I'm showing you here are done in 10 minutes, something like that. Now, I mean, random forest also can have a scaling if you start to do larger data sets, but I think both of these will be pretty doable without having to use any kind of high performance computing for data sets less than 1,000 individuals.
Forest, are you using the bins each, the chunks in the windows, or are you using the complete chroma?
The random forest, the user has the option of specifying how many adjacent markers do you want to give the classification algorithm. So you can play with that variable. I've used the 100 closest markers to give it as possible predictors. I haven't explored a lot whether going higher than that would lead to much better results, but that's a variable you can adjust easily with the function. You saying you've used the entire chromosome? Okay, well, that's good to know. Thank you. Anything else? Okay, well then we will switch to talking about coma, which is something quite different. Maybe, let's just stick around.
Chris.
But how do you get the right screen to display?
Yes, you need to share. This first. Okay. I got the pattern yesterday. For the second here.
Give it a minute. Okay, it's coming.
Good.
All right.
You got it.
Thank you. Right, so COMA stands for Convex Optimization of Mate Allocation. And thank you to funding from USD and NIFA for this project. What is mate allocation? Not a term that is widely used in plant breeding. It comes from animal breeding, but of course it means the same thing whether you're talking about plants or animals. It's about mating individuals to create progeny for the next generation. So mate allocation is basically the genetic contribution of any particular mating to the next generation. For a plant breeder, that would mean a list of the crosses and how many progeny per cross that you're going to be planting out for your next cohort of your breeding program. Something that every plant breeder has to do. And the question is, how do we do this? I think probably those of us who are practical plant breeders have some combination of, we have some rational basis for doing it, then we have some traditional things that it always done that way, so we're not really sure if that's the best way. And this is all about trying to put as scientific a footing to this process as one can. So the concept of an optimum mate allocation is this: you want to maximize the genetic merit of the next generation. That's what selection is trying to do. But you have to be careful because you need to worry about inbreeding when you're talking about an outbred species. And as polyploid crop breeders and even diploids, we're talking about outbred species in this community. And if you start to mate two closely related individuals, you're going to see the loss of genetic diversity over time. And that's something that we have to guard against. So breeders in practice kind of know this intuitively, but then this is a way of formalizing just exactly how far can you push mating related individuals without worrying about your inbreeding going too far. So that's the nutshell description. It's a balance between the short term and the long term gain. If if you were going to finish your plant breeding career next year, you would simply take the 2 best individuals, mate them, and you would have the best progeny possible. And then the next breeder is just really in trouble, right? Because then they don't have very far to go from there. So in particular, like when I started using genomic selection, my naive idea was I would just do a ranked list of my clones, draw a 10% line, and then just start mating them. And again, you'll just find you deplete genetic variants too quickly if you do that for any length of time. So in animal breeding, who've been doing this for many decades, even before genomic selection, they had to worry about this with their pedigree-based blood methods. They've developed some guidance, and a typical number you'll see in the animal breeding literature is about 1% inbreeding rate seems to be as fast as you want to go for inbreeding. And there's some, I think, just decades of experience plus some theory that goes into that. I've done some simulations which seem to actually confirm that's a reasonable target. So that's kind of nominally what I'm going to use for this presentation. Here's a picture just to show that in an actual simulation. Here's a plot on the y-axis of the genic variance, which is related to genetic variance, is the proportion due to allele frequencies and not due to LD, for 3 different inbreeding rates. The red one is an inbreeding rate of 0.05 or 5%. The green one is 0.2%. And you can see by 10 cycles, you've lost, let's say, half of your genic variance with a 5% inbreeding rate. Of course, you get the most gain over those 10 cycles, but then what do you do the 10 cycles after that and the 10 cycles after that? So that's what we're talking about. And this is work done with Alpha Samar, a very nice software for simulating breeding programs. Okay, inbreeding rate. I'm using that term, and you probably don't know exactly what I mean by that. It's not what I thought it was when I just kind of started learning about this. Inbreeding coefficient is something that probably you do have a sense for. And the one formal definition would be the probability that 2 genes at a locus are identical by descent. We had a nice conversation at dinner after a drink or two about IBD versus IBS. And I don't think that's actually the critical point here. The critical point is that this is a probabilistic measure of inbreeding. And that's the key thing, because the next equation depends upon what's called the law of total probability. And that's the definition of inbreeding rate. Confusingly, I think, is that the symbol delta F is universally used by animal breeders, whereas the symbol delta usually in math is like the difference between 2 things. And it's not the difference between the inbreeding coefficient of 2 generations. That's what naively you would think delta F stands for, but it's not what's meant here. Delta F is, in words, it's the amount of new inbreeding that occurs in each generation. So this is the law of total probability expression, which you can find, for example, in Falconer and McKay. It's just textbook material. The inbreeding coefficient, let's say, of the T+1 generation, which is the probability that 2 genes selected at random are IBD. There's 2 possibilities. Those 2 genes that you selected were essentially the same gene in the previous generations. The duplication happened in the immediately previous generation, and that occurs with probability delta F. That's what delta F is meant to mean. And if that's the case, then they are IBD with probability 1. So you don't see it here, but there's a 1. That's the probability of IBD conditioned on the fact that they were duplicates that they were the same gene in the previous generation. And then this other part is the other conditional probability. It occurs with probability, you're conditioning on the fact that they were not immediately duplicates. That happens with probability 1 minus delta F. And then with probability F, they are IBD from previous generations. If that didn't make any sense, it doesn't really matter to you. This is the kind of equation that can relate inbreeding coefficients across generations based on this concept of a rate. So now we need to relate the inbreeding coefficient of the next generation, the one we're trying to design or optimize, based on the inbreeding coefficients related to the matings. So let's define a set of mate allocation variables. That's what this symbol X sub ij represents. It's the contribution or the allocation of that particular mating between individuals I and J is going to represent in the next generation. And those proportions have to add up to 1 because you're completely allocating all of your resources in the next generation. And it's just a weighted average of whatever those inbreeding coefficients are for every given possible mating. That's going to tell you what the inbreeding coefficient overall is in the T+1 generation. So with that kind of mathematical preliminary, we can write the optimum mate allocation problem as follows. We have a set of unknowns, X. Those are our decision variables. Those are the allocations that we're trying to decide. And we're trying to optimize the genetic merit of the next generation, which is the merit of any given mating. That's what I'm using the symbol H for here, which would be the mean of all the F1 progeny from a particular mating. You could also think of versions that take into account the variance of a particular mating, but this formulation is based only on the mean value of the progeny. And again, it's weighted by whatever your allocation is. And then you have the inbreeding coefficient has to be less than or equal to this right-hand expression, which is based on whatever your current inbreeding coefficient is, and this rate, delta F. If you look at this equation, you'll see it has a linear objective in terms of the unknowns X, and this is a linear inequality, again, in terms of the unknowns X. That is one of the hallmarks of a linear program, which is a type of convex program. And as it turns out, but constraining the inbreeding rate for one generation turns out to be not quite sufficient to actually constrain inbreeding in the long term. You have to constrain the inbreeding rate for both the next generation and the generation after that. And I don't want to give you a completely intuitive explanation right now as to why that is, but we can get into that maybe in the break. The equation for the next generation is nonlinear, but remains convex, as it turns out. It's a quadratic convex expression. And so nonetheless, you can still use these convex solvers to solve the problem efficiently. What does convex mean? For those of you who never heard that before, convex, think like a parabola. Okay, parabola has a single global minimum, and it's smooth. So you can use kind of a descent algorithm to find that global optimum efficiently. This is what there's a whole branch of mathematics and computer science that deals with this. So we don't have to reinvent that wheel. We just have to learn to make our problems fit into the mathematical framework that already exists. The nice thing about this is that once you have this set up, you can add additional inequalities that allow you to incorporate a variety of practical constraints. And I'm going to give you some examples of that here in a minute. So before I get to the vignette, there's one last piece of information I want to share with you is that optimum mate allocation is already an extension of an older algorithm in animal breeding that's called optimum contribution selection, or OCS as the acronym. And the difference is that OCS took the contribution of the individuals as the decision variables, not the matings themselves. It assumed that once you optimize, let's say this individual represents 20% of the next generation, it assumed that you just randomly mated those individuals to develop the mating plan. And the optimum mate version of it allows you to get beyond random mating, and so you can actually do better in terms of balancing the trade-off between genetic gain and diversity. So I'm going to be in the vignette, you'll see I'm using optimum contribution selection as an interesting baseline for comparison for those people who may be coming from animal breeding and are familiar with that. So the vignette is available on the GitHub site. So there's now a new repository on my site called Coma, and it has a short vignette illustrating the basic functions of the package. So the first one is to read the data in. It's interesting how many people are now using read data. It's such a generic name, but it just fits the purpose really well, right? So here's the read data function for Coma. You have to have a genotype input file, which starts with the marker effects, and then it has all of the allele dosage data for your parental candidates. I decided to separate the problem of genomic fitting the prediction models from the optimization. So you're going to have to use some other software to come up with the marker effects. Stage-wise, of course, is a good option, and this program was written based on the parameterization and stage-wise, but of course you could find other parameters, other software that may be able to do that same kind of parameterization. More on that in a minute. The kinship file is an n-by-n kinship matrix. You can give it any even integer ploidy, and then if you're working with a dioecious species, which I've not done extensive testing on because I don't work on one, but in theory, the math should allow you to also deal with the fact that you have different male and female individuals. So if anyone has data like that, I'd be very interested to have you try this out and let me know if you find any problems. And then the matings option has a couple different, the matings argument has a couple different options. So we'll come to that in a second. So here's the example genotype input file that comes with the package. There's 93 potato clones. I have used stage-wise to analyze a lot of historical data for our breeding program. I built a selection index that combined yield, dry matter, potato chip color, maturity, and put it all into the package and got these additive and dominance marker effects. And it includes a estimate of inbreeding depression. The inbreeding depression is built into the dominance marker effects. So that is, I think, something that increasingly we should be considering when we build our prediction models. And then the dosage data is just standard zero diploidy. It doesn't have to be integers. And as I say here, you can use the BLUP function in stage-wise to get this kind of information. What about the kinship file? So really the best approach for doing this would be to use what I would call realized IBD kinship. It would be if you actually took a pedigree and you were tracking individual haplotypes from the founders, and you could calculate your kinship matrix based on that. There's no software to do that in a tetraploid or higher ploidy yet. That's something that we're thinking to hopefully do in the next couple of years. So what can you do instead? Well, you can use like a Van Rayden type G matrix, and in which case it's essential that you use when you center your markers, you use the base population allele frequencies, which for example is not what's done in the RBLUP package. So don't just go run the RBLUP package and expect it to give you the right answer. And I think this is what Tim's going to be talking about here shortly. So that's what animal breeders do. And that's what I had expected to do. In fact, interestingly for me, though, when I started to do simulations, I noticed that using this approach, you still don't get the right inbreeding rate. And I believe the reason is that the inbreeding coefficients calculated from these types of G matrices are not probabilistic interpretations of inbreeding. They're correlation measures of inbreeding. It's a whole separate conversation. But as a result, those constraint equations don't actually apply for inbreeding coefficients derived from G matrices. So that's not ideal. On the other hand, what I have been doing is also not ideal because I'm just going to use a pedigree relationship matrix, which doesn't account for different rates of inbreeding potentially among different loci in the genome. But nonetheless, that's what I have for you in the vignette. It's a kinship matrix calculated from the AGH matrix package. And the formula is simply you take the numerator relationship matrix and divide it by the ploidy, and that's your kinship matrix. Okay, so here is the call to read data. As I mentioned a moment ago, there's this argument matings, and one of the options for matings is just all, which just means it just generates a list of all unique combinations of the parents that are in your input files. So for the 93 potatoes, there's some over 4,000 possible combinations, and it is going to make it gives you the predicted merit of all 4,000 combinations based on those additive and dominance marker effects. It also then gives you the GEBVs, which is what is meant by merit when you talk about just an individual parent under a random mating scenario. So that's the output from the read data function. And then we go immediately to step 2, which is to call the either OCS or OMA function to generate the optimum contributions or the optimum allocations. So let's look at OCS. The OCS function takes as the first argument inbreeding rate. So that's what DF. This is an example of inbreeding rate of 0.5%. And the parents argument is you get from the read data. That's what the data parents part here is. But then you have to additionally add something which is, it tells it what are the minimum and the maximum values for the contribution of every individual in the population. Here I'm going to give values of 0 and 1. Okay, those are the mathematically extreme as possible, but you can also add additional information. I mean, I have had many situations that I've encountered in the last couple of years using this software where I had an individual that I just ran it like this, and it wasn't selected because based on the index that I had previously computed based on fry color and yield, it just wasn't, it didn't optimize the next generation, but it had some other characteristic that wasn't in my prediction model and that I really wanted to have. So I just gave that one individual minimum contribution of something greater than 0. I could say I want at least 5%, for example, or whatever it is. So you can force it to take in ad hoc information from other traits because our prediction models are never going to have everything that you care about as a breeder. I mean, it's just not realistic. So this allows you to add that additional context to get a completely practical and optimized mating plan. Okay, so that's the syntax for OCS. It's what you see right there. And then OMA is very similar, the difference being that it has to have now not just the parental limits, it also needs the limits for every mating. What's the minimum, the maximum that you will allow for any given possible mating? And again, if there's a reason why you want to have something different than 0, 1, you can do that. But here I'm just going to use those extreme values. So what do you get out? So here's 2 successive calls to the OCS function. The first one with the inbreeding rate of 0.5%, and then we're going to double that and make an inbreeding rate of 1%. And based on what I've told you, you'd expect that you can get a higher genetic gain if you allow more inbreeding, and you can see that's what you get here. The one part of the function returns is this table called response. I just put those 2 responses together, and I see at an inbreeding rate of 0.5%. The average predicted merit is 1.79. This is in units of genetic standard deviations. I forgot to mention this, but there's this argument standardize right here, which if you want to re-standardize everything so that your responses can be interpreted in terms of genetic standard deviations, that's what it does. Otherwise, it keeps it in whatever units your additive and marker effects are in. So you get from 1.79 to 2.01. So you get a higher response if you allow higher inbreeding, but your diversity goes down. This diversity is the Shannon diversity. That's like an entropy definition. So a completely, if every individual has exactly the same proportion, that's the highest possible diversity. And then if there's only one individual, you have no diversity, right? So you get less diversity as you go to a higher inbreeding rate, exactly as you would expect. What about with the OMA? It looks like a similar kind of output. There's a merit and a diversity, but now there's these 2 different inbreeding rates. Now, these values, it's not so obvious right here. These are not the input values. This is actually the realized inbreeding rate of the solution that it found, which needs to be below the target if the software is doing its job. So this is a check on that. And here you see explicitly the DF1 is the rate from the current to the next generation, and the DF2 is to the generation after that. I mentioned a moment ago that you actually have to put both of those constraints on it to properly control inbreeding. And we're going to see why that is here shortly. So that's one part of the information is this response table. Oh, I guess here's a simple piece of code that uses lapply to just give it a wider range of inbreeding rates instead of having to copy and paste all the function multiple times, which is probably the first thing you do if you're new to R. Here's a way of giving it a whole vector of inbreeding rates and seeing what comes out of it. So now I've added in the PowerPoint, this table in blue is what the input was. And now you see in this color scheme what the realized inbreeding rates are. Notice that the inbreeding rate for the next generation at the low targets, we are hitting the limits. It's still, we specified 0.5% and it hit the limit of 0.5%. But once we got to a point to a 2% inbreeding, notice that we actually didn't quite hit the limit for DF1. We hit the limit for DF2. And when we went to 3%, again, we didn't hit the limit for DF1, we hit the limit for DF2. So you have to really worry about both of those constraints to get reasonable solutions. The merit is going up progressively as we allow more and more inbreeding, and the diversity is going down progressively. What about the allocations and the contributions themselves? So these functions return not just that response part of it, but they also have a component of the list that has the name OC for optimal contribution or OM for optimal mating. I guess I could have called it OA now that I think about it, but that's what I came up with. And so for the OCs, it's the names of the individuals and what their contribution is to the next generation. So I look at this individual, 1912-12, its contribution is 0.15. If we look in the matings, we see that these first 5 matings all involve that one individual as one of the parents. And so if you add up all the values here for every mating that involved that parent, I'll add these all up, you should get what the value is right here. Multiplied by 2, I guess, or divided by 2. So that's a numeric way of looking at it. You can also make nice visualizations with this plot ribbon function that I wrote, which is a wrapper around some ggplot2 output. So this is showing you on the y-axis, it's just stacking up Every color is a different individual here, and you can see how that there is something like 30 different parents were selected to contribute something at an inbreeding rate of 0.5%. And when I go up to an inbreeding rate of 3%, I'm down to like a third of them. They start progressively dropping out as I allow more and more inbreeding, because it doesn't need that much diversity. It's just going to start focusing the design on the superior individuals. And you can make a similar kind of plot for the individual matings as well. Again, you have many more matings when you have a low inbreeding rate, and as you allow more inbreeding, the number of matings it selects goes down because it's just picking the matings that have the highest merit. Okay, so now let's look at some additional constraints that you might want to add. So in this potato example, there are two additional constraints that I've had to consider in the real world. One is that we have male sterility rampant in our potato germplasm because it has been associated with certain resistance traits that we've introduced from wild species, one of which is the one I'm showing you right here, this potato virus Y resistance. So for years, we've been selecting for potato virus Y resistance, and we're bringing in a cytoplasm that's actually causing a lot of male sterility. So I have given you a file in the vignette that shows for all the 93 individuals, whether they have the genetic marker that indicates they are CMS, cytoplasmically male sterile. It's not validated, but that's what the marker would predict. And the marker for the PVY resistance. So the idea is that I'm going to, instead of giving the mating, the OMA software, all possible matings, I'm going to eliminate matings where both parents are CMS. You could never actually make that cross because at least one of the parents has to be male fertile for that mating to be made, right? So that's one constraint I'm going to add. And also this PVY resistance is like a must-have trait for us. So I don't want to make any matings where at least one of the parents doesn't have. I don't want any matings where neither parent has the resistance. At least one of the parents has to have the resistance, and ideally both, because then I get even higher frequencies in the offspring. So it's a couple lines of code to do that. You have to know a little bit of R, but here's an example. I say, for example, the first line is the test for PVY. I say that either parent 1 has to be in my PVY resistant list, or parent 2 has to be in the PVY resistant list. That's the requirement for PVY, the virus resistance. The CMS test says that I cannot have both parent 1 and parent 2 in the CMS list. The exclamation mark is the not logic. So I subset my original matings based on this test, and I reduced the number of matings from 4,371 to now 3,119. So I've thrown out 1,000 matings that I don't want to consider for these reasons. You run the OMA software using the updated matings list, and you get the best solution under those constraints. And we've reduced our merit from, originally it was 2.04, now we're down to 1.77 by adding these additional constraints. So you can't do as good, but you know, you can't do as good with respect to those quantitative traits, but I'm adding these other traits that are equally important. And here's another example. So even though I have even though I've ensured every cross has at least one parent that is not CMS, okay, that has to be the male parent. If all of my matings have a female CMS parent, then the entire next generation will be CMS, right? If all the females have that cytoplasm, then I'll have no males in the next generation, and you know, I'm retired at that point. So that doesn't work either. So I have to furthermore constrain what's the total contribution of CMS individuals to the next generation. And you can do that quite easily. So I can, this is a little bit of code that actually checks this. The previous solution we just found, 40% of all of the total contribution is coming from CMS parents. Let's say we want to limit that to 25%. So you add another column to that parents table, which shows for every parent what's the minimum and the maximum. I'm going to add another column, and the values in that column are a coefficient vector when taken the dot product with the unknowns, which is the parental contributions, I want it to be less than or equal to 0.25. And it knows that that's what the header is. So you name the column LT or GT or EQ, depending on if you want it less than, greater than, or equal to whatever that numeric value is. And it just starts to add more and more equality or inequality constraints to the optimization. So here's the OMA with this new constraint. Again, the merit now has gone down as it has to because I've added more limitations, but it's still not a big change for what I think is a real win, which is limiting how much CMS I have propagating in my program. So to me, this software is, I think, one of the best things that I've created, to be quite honest, in terms of practical plant breeding. Genetic mapping is great, but this provides the tools to really develop practical mating plans for genomic selection. So I'm really excited to have many of you try this and give me some feedback. And I've done a lot of simulation testing of it with the Alpha SIMR program. I'll be talking about some of those results at the potato genomics workshop on Tuesday at 10:30. So hopefully I'll see some of you there. Thanks for listening.